Here I've got a nice integral that was suggested to me by someone that I'm calling the integral suggester. So this is the integral from 0 to infinity of x minus sine x over x cubed dx. And we're going to use the following well-known fact. And that's the integral from 0 to infinity of sine u over u du is pi over 2. I think I've derived this on the channel before if you want to try to find that. Okay, so let's get to this. So how are we going to do it? Well, I'm going to re-represent this single integral as a double integral and then a triple integral. And that'll put it into a form that looks like this, and then we can finish it off from there. Okay, so let's first notice that this looks like the integral from 0 to infinity of xy minus sine of xy over x cubed, where we've evaluated this from y equals 0 to y equals 1. Notice putting in y equals 1 gives us this exactly. Putting in y equals 0, well, that just gives us 0. That means that we can take this object right here and take its derivative by y and replace that with a definite integral. So that'll give us the integral from 0 to infinity and then the integral from 0 to 1 of x minus x times cosine of xy all over x cubed dy dx. So what did I do from this step to this step? I just took the derivative of this guy with respect to y, keeping in mind that I need to use the chain rule right here. But notice I get a little bit of simplification. I can take this and rewrite it as the integral from 0 to infinity, the integral from 0 to 1 of 1 minus cos of xy all over x squared and then dy dx, where I just let those x's cancel. Now I'm going to do the same kind of thing again. So I'll notice that this looks like the integral from 0 to infinity and then the integral from 0 to 1 of cosine of xz over x squared, where we've evaluated z from y up to 0 dy dx. So let's make sure that makes sense. So plugging in z equals 0 will give us cosine of 0, which is 1. That's good. Plugging in z equals y will give us cosine of x times y, and that's good too. Now we can take the derivative of this guy with respect to z. So let's write that out real quick. That's going to bring another x down in front, and then we'll have the sine of x times z over x squared, but we'll also have a minus sign because the derivative of cosine is minus sine. Well, I can take this x right here, cancel this exponent out, and then I can take this minus sign right here and use it to flip the order of the bounds of integration. So that's going to, in the end, give us the integral from 0 up to infinity, and then the integral from 0 to 1, and then the integral from 0 to y of sine of xz over x, and then we have dz dy dx. So that's looking good. We'll do one last thing before we move everything to the top, and that is to move this infinite integral all the way inside. So then we'll have the integral from 0 to 1, the integral from 0 to y, the integral from 0 to infinity of sine of xz over x, and then we'll have dx dz dy, like that. Okay, so now let's bring that up here, and we're almost ready to finish it off. So on the last board, we ended up with the following triple integral that has the same value as our goal single integral. Now we're about ready to finish this thing off. So our next step will be a u substitution. So let's let u equal x times z. Notice that that means that dx will be equal to 1 over z du after moving some things around a little bit. Furthermore, as if x is equal to 0, u is also equal to 0. And as x approaches infinity, u is also approaching infinity. And that's, of course, with the understanding that z is between 0 and y, where y is between 0 and 1, so all of those limits make sense. Okay, so let's see what these things look like within the integral. So here this xz is being replaced with u. Then this dx is being replaced with du over z. Then furthermore, this x can be replaced with u over z. But notice that this z here can cancel with this z here. So that's pretty nice because now we don't have any z's or x's left. So just to reiterate what we have the integral from 0 to 1, the integral from 0 to y, and then the integral from 0 up to infinity of sine of u over u, du, dz, dy. Okay. But let's notice this innermost integral doesn't have anything to do with the outer integrals. And furthermore, it's exactly the form of this tool that we said that we would use. So we can replace this with pi over 2. Then I'm going to rewrite this as pi over 2, and then the integral over a region which I'll call triangle dA, where this region triangle is in the zy plane. So let's draw a picture of it. So let's notice the y value is going between 0 and 1. So I'll put a 1 here on the y-axis. And then the z value is going between 0 and y. So I probably want to draw the graph of z equals y here. Let's notice that our region that we're doing this double integral over is that triangle. And that triangle pretty clearly has a base of 1 and a height of 1. That means it has an area of a half. So we get that our final answer is pi over 2 times the area of this triangle, given that this is just really a double integral giving us the area. But like I said, the area of that triangle is a half. So multiplying pi over 2 by a half, we get pi over 4. So in the end, the value of our goal integral is pi over 4. And that's a good place to stop.